Okay, good evening, students. Salams. Okay, so today, yeah, I'm starting a class for English. These first two sessions are going to be free. Okay, first two sessions are free of charge. So, yeah, it's fine. Yeah, we will be like conducting the sessions like frequently, but I started a regular class because students asked me to do. It was my dream from the beginning to start English medium classes. I was teaching for Tamil medium, so now my dream came true. So let's start discussing the 14th paper. I have already informed you all about what we are going to discuss today. That is 2014 paper. It's mentioned. It was mentioned in the poster itself. No, I put that in on my YouTube and my status, so that you could have seen that. So now we are going to discuss 2014 paper. So we can also discuss the structures and essays also, but usually students, they understand by just going through the schemes for structures and essays. But for MCQs, you need some sort of an explanation. And if you find any trouble in the audio, just let me know, because sometimes this microphone creates metallic noise which is very disturbing. Okay, let's start. So first question: as far as the units are concerned, which of the following quantities differ from the rest? So this is very simple. So first, rotational kinetic energy. You know whether it's rotational or not, it's energy. Yeah. So it has the unit joule. Okay. Joule. It is equivalent to Newton meter also. Where does this come from? This comes from work. You know the equation for work. Work is force into the distance moved. I mean, to be positive, both should be in the same direction. Okay, it's not a vector, but there is a sign convention. Okay, now, so this has meaning of Newton meter, so Newton meter. So it is equivalent to joules. Okay, but we don't express energies in Newton meters, only the work. But work can be expressed in joules. Internal energy, mechanical potential energy, work, all are same. But power is actually energy per second or work done per second. Okay, so that has unit of joule second minus 1. What is the other unit? Special unit for that. You can unmute and answer. What? WATT. So this is the SI unit for that. So do you know about internal energy? Something that is mentioned in the third answer. Is it new to you? Internal energy? It's not new to you. You study about internal energy in thermodynamics. Okay, internal energy is something that a substance possesses due to its molecules. The molecules have two types of energies. One is kinetic energy, the other one is potential energy. Okay, kinetic energy and potential energy. So kinetic energy is due to the motion. You know, when you take a mass, it's half mv square. If it is a linear motion, and if it is a rotational motion, you can express the kinetic energy this way. And what about potential energy? What is the main determinant of potential energy between molecules? Huh? What's the determinant? What's the factor? Yeah, potential energy is directly relatable to the attractive forces. Okay, attractive forces, intermolecular attractive forces. Okay, so we study the internal energy for ideal gas. For ideal gases, you know that there is no attractive force or a repulsion force. It is only the kind, so there is no potential energy in it. So it is only the kinetic energy that is responsible for the internal energy of an ideal gas. So I'm asking a question now. Can you increase the internal energy? Okay, now imagine a container with an ideal gas and normal gas. So now I am taking this and running on, okay, running with the velocity. So what will happen to the internal energy of this ideal gas? Because I'm running, it has a velocity now. Okay. What would be the change in kinetic energy? Increases or decreases or constant? Huh? I can't hear you. Can somebody unmute and speak? Students? Also say loud enough. It's not loud enough. Okay, so I can just remove it. This microphone is very low quality. Okay, now we shall test it again. Okay, so unmute and tell me, okay, if there is any trouble. Okay, now what about my audio? Is it better?
Yes, sir, better.
It's better. Okay, thank you. So this microphone was bought for $0.01. So we can't expect much quality. But it's okay. It's okay. It's a very good microphone. Okay, so what will happen to the internal energy here? Huh? Will it increase? No, it will not. Okay, speak up. Okay, so it will not change because the internal energy is only depend on the temperature. Okay, temperature. It's directly proportional. We express it as U. It's directly proportional to the Kelvin temperature. Okay, thermodynamic temperature. Kelvin temperature. So here, that's the theory. It is not dependent on the external motion. Okay, so that is that's an introduction for internal energy. So let's go to the second question. Which of the following quantities is or are dimensionless? So you know the relative velocity. Relative velocity. What is the equation for relative velocity? So if I say velocity of A in relation to so in relation to B, we write it as A comma B. No, so what is the equation for this velocity of A in relation to B? It's VA minus VB, isn't it? Okay. So usually when you have some relative thing, okay, it is expressed as a fraction. For example, relative density, okay, relative permittivity or relative humidity, okay, in all those instances, yeah. In all those instances, there's a fraction, but here it's only subtraction. Okay, so the relative velocity, the answer is going to have a unit, which is also ms minus 1. But the second answer is relative density. Density is the density of the object over density of water. Okay, so this cannot have a dimension or a unit. And C, relative humidity. Humidity, what are the equations for humidity? RH, can you tell me one equation? Mass of the water vapor, unsaturated water vapor in a particular volume at a particular temperature upon Mass of the saturated mass, that is mass of water vapor that is needed to saturate that particular volume at particular temperature into 100. Or we can express it as like as AH over AHS also. Here AH means the mass of water vapor per unit volume, and this is the mass needed to saturate a unit volume. Okay, this is very easy because it is not dependent on the volume, because we are expressing it for unit volume. So I usually use this one. Okay, what are the other equations in relation to pressure? Okay, unsaturated vapor pressure over saturated vapor pressure into 100. And what is the other equation that you apply in the practicals?
Density.
Density. This is the density thing. AH over AHs. Saturated vapor pressure at PS at dew point upon divided by what? PS at room temperature. Okay, room temperature into 100. This is what you use in the RH practical. Okay. So all these are according to all these equations, the RH doesn't have a dimension. So it is B and C, the correct answers. Okay, not A. So which of the following, the third question, which of the following propagate in the form of longitudinal waves? So there are two types of waves according to the nature of the oscillation of the particles or the field. Okay, so what are the two types? Longitudinal, the other one transverse. So in transverse waves, we have two main entities. One is what? Electromagnetic waves. All electromagnetic waves are transverse waves. There you don't have particles oscillating. There are fields, two fields. What are those two fields? Electric field and a magnetic field perpendicular to each other. Okay, propagating in the direction of the energy transmission, and also perpendicular to the energy transmission, and in the same phase. Okay, in the same phase. Both fields are in the same phase. And transverse waves also consist mechanical waves also. Can you tell me an example for transverse mechanical wave? Strings you have, no? Okay. So longitudinal waves, here the particles move parallel or anti-parallel to the direction of the transmission of the energy, but here perpendicular. Okay. So that is an introduction. So first, laser light. So laser light is what? It is electromagnetic wave. Okay. It is not included in our spectrum because we produce according to our needs. Okay. We can't actually say a specific frequency or wavelength for laser. X-rays. X-rays are, yeah, you know, X-rays are between the gamma and, so first gamma, then X, UV, and visible rays, and IR. Then you have that order. Okay. Ultrasonic waves. What are ultrasonic waves? Ultrasonic are
Type of sound waves, sir.
Sound waves. Yeah. What is the definition for ultrasonic waves? They have frequency of more than what? Usually more than 20 kilohertz. Okay. Then microwaves. Yeah, microwaves are below IR. Radio waves. Radio waves are below micro. Okay, here you get micro, here you get radio. What are the types of radio waves you know? There are three types. What are those? UHF, VHF, and FM. No? Then you have short wavelength, intermediate and long wave, short wave, intermediate and long. Okay, like that. So this is the electromagnetic spectrum. So the correct answer is ultrasonic wave, third answer. Okay. Then the fourth question. When a guitar is played, it will produce. Okay, first they are talking about the type of wave on strings and then in air. Okay. So what do you have on strings? Huh? On strings? On strings? Yeah. On strings. So when a guitarist when he plays, actually he produces a wave and it will reflect in one end. It is not a structure of guitar, just a string. Okay, it will reflect in one end, and then there will be superposition of the incident and reflected waves. Then you get something called a standing wave. So it is an example for standing wave. Okay, this diagram shows the shape of the standing waves through extremes. One is this extreme, the other one is this extreme. And this is an intermediate state. Okay. So in a standing wave, what are the features of standing wave? On a string, okay, on a string, there are different shapes. You can draw different shapes. Can you all try to derive equations for these overtones? Okay, for 2 minutes. I will give you 2 minutes. Derive equations for the frequencies. There is tension T and you have linear density M. Okay, now deriving equations. It's very important. Okay, so now you have the length has been given as L. So now you can actually write an equation for the velocity of the transverse waves in a stretched string. Okay, it is T over M. T is the tension, M is the linear density. Okay, so and also you know the equation V is equal to F lambda. V is equal to F. Here in the fundamental overtone, the lambda is equal to 2L. Okay, so you can give F as 1/2L and B as square root T/F. Okay, so this is the equation for first frequency of the first overtone. And like that, you can write for here for this also. Here, L is actually equal to lambda. What about lambda here? Huh? This is L. What about lambda? We should divide the L by 3 in two loops. Two loops give lambda, no? So multiply by 2. So divide the L by 3 and multiply it by 2. So 2L by 3 is lambda. So you can derive equations for the first overtone and also for the second overtone. Okay. So this will be like 1/2, 1 over L square root T over M, and this will be like 3 over 2 L square root T over M. Okay. So like that. So these are standing waves. Okay. What are the differences between standing and progressive waves? What about energy transmission along the wave? In standing waves, you don't have the progression of energy. No, it's not transmitted along the wave. It is only the vibration that you have. Okay. What are the other features of this standing wave? Stationary wave. You have nodes and antinodes. Usually, what do we mean by nodes is displacement nodes. Okay. Displacement node. So this is a displacement node. This is an antinode. What are the other features? What about the amplitude of different particles at different displacements? I mean, at different points. Amplitude here is the maximum. And if you see here, the displacement is always 0. And here it has an intermediate amplitude. And this is maximum. So amplitude at different points are different. But in a progressive wave, what about the amplitude? It is same. Okay, it is same for all the particles. Okay. So now, yeah. So this is how a wave is formed on the string of a guitar. Okay. So in standing waves, we said that the energy is not transmitted along the wave. So how do you hear that sound? Any bright answers? How do you hear? Huh? It is not transmitted along the wave, but it can be transmitted to the vibration can be transmitted to another medium. Okay, the air is another medium, so it can be transmitted. Why is that? Answer. Yeah, how do you call that kind of an oscillation? Huh? How do you get the compressions and rarefactions in the atmosphere? How do you get? That is due to the movement. Okay, due to this vibration, you get compressions and rarefactions induced in the air molecules. Okay, that can be transmitted. Okay, it's not the energy that is transmitted along the wave. It is the energy that is transmitted from the strings to another medium. Okay, so that can happen. So here it can travel. The energy should travel in air so that you can hear. Okay, so that should be a progressive wave. And you know it's a sound wave, so that should be a longitudinal wave. Okay. Okay. So now, yeah. the longitude, the transverse standing waves on the strings and longitudinal progressive waves in air. So what's the correct answer? The fourth answer. Okay. Then the fifth answer. The fifth answer, we are going to use that, sorry, fifth question, we are going to use that question for a revision. Okay. So it is about compound microscope. Let's revise the theory of a compound microscope. The compound microscope, why is it compound? Because it consists two lenses, okay, two convex lenses. It is an optical instrument that is used to magnify small things, small objects. Yeah. So there are two lenses. One that is kept near the object is called the objective. The one that is near the eye is called eyepiece. Okay. So you have different focal lengths for these two lenses. So first I'm going to move the focal length of objective as f0. There is 2f0 also. Okay. So now tell me, where do you keep the object in relation to the objective? Quick. Just unmute and answer. Yeah. It's not a very difficult question. You should answer.
Outside the focal point.
Yeah, between f0 and 2f0, no? Yeah, like this. You keep the object. So where do you get the image? In the opposite side, magnified, inverted, real image beyond f0. Okay. It's a magnified one. So this now acts as an object for the eyepiece, and this is within the focal length focus of this eyepiece. Okay, you understand? So within the focal length, now the U is smaller than the focal length. So what kind of an image that you are going to get now? In relation to this eyepiece, what are the properties of the image? Features. Yeah. We can draw it like this, no? An upright in relation to this object. Okay, this object, the image would be upright. Okay, virtual, magnified. Okay, on the same side, So this is the final image. So you should be able to state the features of the final image in relation to the object also, the initial object, the object proper. So it is now inverted, okay, magnified, virtual. Okay, so now this is also a magnified one. So you have something called an angular magnification here. Okay, what is the equation for angular magnification in a compound microscope? Yeah.
1 plus DOF.
Yeah, 1 plus DOF. F what? F. There are two F's. F. E. Okay, it's Fe. And here V naught over F naught minus 1. Okay, do you understand? So this component is actually the linear magnification of the objective. This component is actually the linear magnification of, this objective. This is eyepiece. Okay, both are linear. It's actually the multiplication of those two linear magnifications that gives the angular magnification. Okay, you should be able to derive this equation. Okay, from the basic equation for angular magnification. Okay, you should revise the theory. And it seems like you all are not confident about this. Okay, so it needs revision. Okay, it's my responsibility to point it out. Yeah, now, and you should also be able to draw a ray diagram. Okay, so don't forget the arrows. So that's all. So let's see the statements. So it has two convex lens, obvious. Yeah. Second, image of the object is formed. Sorry, image of the object formed by the objective is real. Yeah, that's real. Separation of the lenses is much greater than the focal length of the objective and eyepiece. Yeah, because the first image is like beyond f2, f0. So the distance should be the distance between those two lenses should be greater than their focal lengths. Okay. And the final image formed by the microscope is a virtual image. Yeah, that's correct. The object to be examined should be placed within the focal length of the objective. No, we should get a real image from the objective. So we should place between f0 and 2f0, not within the f0. It would be a virtual image. So like this. So there is no point in keeping two lenses because one lens has formed the image in this side and nobody is going to look at that. Okay, nobody is going to see that. So no point. The sixth question. Two lenses having an EMF E and internal resistance R are connected as shown in the figure are equivalent to a single cell with what? That's the question. What E and what R? So this is connecting two cells in parallel. Okay, the internal resistances are shown separately, but that is a way of drawing this diagram. Okay, but this exists as a whole inside the.
Excuse me, sir.
What?
Your camera has switched sides, sir.
Okay. So my ancient room is now. Yeah. Okay, sorry. So now the resistance is inside the cell, okay? But it can be shown separately also. So now what do you think? So if this is R1 and if this is R2, okay? This is E1, if this is E2. There is a common equation for this. What's that equation? I mean, if the equivalent for this system would be like this, a cell with E electromotive force and R internal resistance, and the relationship is E over R is equal to E1 by R1 plus E2 by R2. So that's the theory. So it will be complicated, okay, if they give different E's and different R's. But it's very easy, okay, very easy in this question because E1 is E, E2 is also E, equal electromotive forces and equal internal resistances. And there is a relationship for internal resistances also. The equivalent internal resistance is equal to 1 over R1 plus 1 over R2. Like the resistors connected in parallel. Okay. So now it's obvious that the equivalent internal resistance is R by 2, isn't it? Okay. And the E is going to be E. Okay, E is going to be E. You know, when the cells with equal electromotive forces are connected parallel to each other, the resultant would be also E. Okay. You don't have to use this equation here. This is for complicated questions. There is one question in 2019. I can't remember the number. So like this, the question was like this. Okay, E1, R1, E2, R2, and this is earthed when they are asking the voltage of this point. So this is like three parallel cells, okay, which connected because this ring structure has a potential of 0 and this is also 1 point. So these are connected parallel to each other. Okay. So they confuse by giving this diagram, but the idea is very easy. This equation should be applied here. Okay, and this equation also needed. Then only you can actually solve that equation. Okay, they're asking actually E, okay, the point voltage here is the resultant electromotive force of that single cell which can function as the system. So you're asking about E, so you should find the potential here. So E should be made a subject here. Okay, so then you should take this to that side. So you will have to find the equivalent resistance using this equation. Okay, am I clear? So this question is very easy. It's sixth question, so it should be easy. Next question, seventh. Okay, the initial parts will be boring, okay, because these are like very easy questions. Seventh question. Two charged conducting spheres of radii R1 is equal to R and R2 is equal to 2R are connected by a thin conducting wire. After being connected, if the respective charges on the spheres are Q1 and Q2 and the corresponding surface charge densities on the two spheres are sigma 1 and sigma 2 respectively, then they are giving some relationships, equations for the ratios of charges and the charge density, surface charge densities. Okay. So now what is the idea? There are two spheres with different radii. Okay, one has 2R radius, the other one has R radius. Okay, but they have different charges. So one is having Q1, one is having Q2, and they're connected by a wire, a conducting wire. So what is the significance of this conducting wire? Why? What's the significance? Why is that? The conducting wire will maintain
Potential.
the potential equal to these two spheres because it can conduct along what the potential difference. So it will never admit any potential difference. So there cannot be a potential difference in a stable state. Okay, after all the exchanging of charges, flow of charges, they will remain in the equal potentials. If the potential of this sphere is V1 and if this is V2, we have our equations. Okay, we have our equations for V1 and V2. So what is the equation for V1? Common equation for potential of a sphere with charge Q.
Q 4 5 epsilon naught.
4 pi epsilon naught R, isn't it?
Yeah.
So now we are going to relate V1 and V2 like this. V1 is equal to V2. And now the substitution is the only thing you have to do. So for V1, you're going to write as Q1 over 4 pi epsilon naught to 2R. But
2
it's the other way. Q1. R1 is R, no? Sorry. So this is Q1, no? This is Q. Sorry, I'm very sorry. So Q V1. So this is V2 and this is V1. So it should be R, no? Sorry. So V2 is Q2 over 4 pi epsilon naught into 2R. So in the exams, you should not write this thing. You should straight away go to this equation and you should not write this component because you know that it's going to be cancelled. Okay, so you should not write, you should not waste your time. So it's Q1 over Q2 equal to 1 over 2. Okay? Okay? What? Are you all clear?
Yes.
Yes. Now we are going to compare the sigmas. Sigma is surface charge density. So sigma is equal to Q divided by the surface area, 4 pi r squared, isn't it? So here you have squared of r. This is r into r. Okay, r into r. So I'm just going to convert this equation. Okay, now see q1 over r is equal to q2 over 2r. Okay, now I'm going to multiply by r in the denominator and the numerator. Okay, I'm going to multiply the numerator and denominator by r here and by 2r here. So the equation remains balanced, still balanced, but you are just changing the things here. Okay, okay, you are inserting some new thing here. So this gives you r squared, and this also gives you r squared. So this is now, these two are now sigmas. So this is sigma 1 into r, and this is sigma 2 into 2r. Sigma 1 over sigma 2 is what? 2. Okay. I should write 4 pi by, but I know my seventh knowledge knows that it's going to be cancelled. So I don't put 4 pi to both sides. Okay, it's waste of time. So I just put r square. I just have to get this r square. So I just multiply the numerator and denominator by same number. Okay. So the answer is third answer. So now I'm going to give you an exercise. Okay, yesterday one of my students asked me this doubt. So there are two spheres like this, hollow spheres. Okay, both are charged, and this one has charge of Q1, and this outer shell. Okay, both are shells. So this can be a solid also. Okay, but the outer one is definitely a shell or hollow sphere. So they have charges Q1 and Q2. Okay, this is A and this shell is B. Okay, so now they are connected by a wire. So what are the final charges on A and B? We can put it in the chat. We shall see. You can put the answer in the chat. Yeah, good. One person has mentioned correct answer. So you know, yeah, these two shells. Yeah. Now here the situation is different. Okay, there is a theory. There is a theory. Okay, what theory? The potential of the outer surface of sorry, the potential of the outer surface of a shell is the potential of the of the volume that is contained in that shell. Okay, the whole volume will have the same potential as the surface. Okay, so now before connecting, okay, before connecting, this had a potential, sorry, this had a charge Q1 and this had Q2. Okay, so what's the potential on the surface of B?
So
Yeah. Hello. Hello.
So your volume suddenly went down, sir.
Hello. Now it's okay.
Yeah, okay.
Thank you. So now, okay. Now, what did I say? Yeah, the potential of the B is VB is Q2 over 4 pi epsilon naught. We shall take the radius of the B as R2. So it's going to be 4 pi epsilon R2. What's the potential of A? BA is equal to Q1 over 4 pi epsilon naught R1. We shall take the radius of the A as R1. Okay, but it's wrong. This is wrong. Why? Because I have only considered the charge on the A, but there is always a potential due to the outer charge also, the charge on B. Okay, so this potential of B should be added to all the points inside that shell B. Okay, A is inside B, no? So this should also be added. 4 pi A0 R2. So when you connect these two, obviously the VA will always be higher than the VB. So it will transmit charges to this. So always, sorry, this should be Q2. Sorry, always the charge will flow until this A becomes uncharged. Why? Because it doesn't need an extra, it cannot have an extra charge, because if it has an extra charge, it will always remain, it will always has a higher potential than the B. Okay, because what that is there on B is already there on A. So there cannot be an extra charge on A. So A loses everything. So QA will be 0, and finally QB will be Q1 plus Q2. Everything will come to this sphere. Okay, you all understood? So now the voltages or the potential of the A and B are now same. Okay. Okay. Next question. 8th question. 4 particles, each having a charge of plus Q, are placed on 4 vertices of a rectangular pentagon as shown in the figure. The distance from the center O of the pentagon to a vertex is A. Electric field intensity at the center of the pentagon is. So electric field density. Yeah, electric field intensity. This is a regular pentagon. Okay, it has, so except E, everything has plus Q's. Okay, so now this is the center of the pentagon O. Okay, so now, yeah, just imagine. First, we shall imagine a charge plus Q on E also. Okay, so now let's draw the directions of electric field intensities due to these individual charges. So due to Q plus Q, it will be like this. Due to this plus Q, it will be like this. So it's going to be horizontal, okay? So like this one like this one like this, okay? The angles between all these directions should be equal, okay? So it cannot be 90 degrees, it's 72. Okay, am I correct? So now if you think about the resultant of these separate the individual electric field densities, what would it be? The resultant. This is actually like a force, no? Force. It's actually a vector, so you can draw a vector diagram. So I'm going to draw a vector polygon. I'm going to try. So now this should be, yeah, we draw this line like this, and then this one like this, and this one like this, and this one like this, and this one like this. So they will complete a pentagon. So they will be in equilibrium. Am I correct? So now just remove this plus Q from this diagram. Okay, so if you remove this particular vector is now removed. So you should erase it. So I'm going to erase it. Yeah, where? Here. So now in this vector diagram, there will be a resultant. There is no equilibrium here. So according to the vector theory, we know what's the resultant. So this is A, B, C, D, E. The resultant is now AE. Okay, AE. So here this is O. Okay, so this should be O. The center is O. So now if you take the direction, so it will be in this direction. This is the direction of the resultant. Am I correct? So OE direction. The resultant is actually electric field intensity by a single charge. Okay. So this part. So what is that? Q over 4 pi epsilon naught A square. Okay. So it's very easy. So you should know two things. One is if you have the equal charges on the vertices of a regular polygon, the resultant will be 0. If you remove that particular one charge from one vertex, the resultant will be through that particular vertex. Okay. Okay. The next question. A thin ring of mass R and radius capital R is rotating in a horizontal plane about an axis passing through its center perpendicular to its plane with a constant velocity of omega. Now, if two small masses each of mass small m are attached gently to the opposite ends of a diameter of the ring, the new angular velocity of the system is. So it is a very familiar question for all of us. So now it is rotating with a constant angular velocity. Omega. Okay. So it's a ring. So now two masses come and they join the system like this. So there will be an increase in the moment of inertia. Yeah, we not apply our law of conservation of the rotational momentum. Okay. Okay. So now, yeah, the initial angular momentum is I initial omega initial equal to the final, I final into omega final. So this is the idea. So what is the initial moment of inertia? Yeah, for a ring. M R square. Yeah, we know the moment of inertia for a point mass, okay, in relation to an axis, for example, O, that is, the distance is R, you know, that is r squared. So like that, you have small point masses which finally culminate into a string, sorry, a ring, so that the same equation for the ring also. Then omega is omega initial is omega. I final is m plus there are two m's. Okay, they will create they will add some moment of inertia, that is 2m into r square. Okay, so these individual moment of inertia should be added. So mr square 2mr square into omega n. So it's very easy. What's the answer? The first answer. Okay, so if we make it subject, the first answer is the correct answer. Then 10. So we are going to discuss it a little bit. The 10th question. A particle of mass small m is dropped freely from a location at a height h0 from the ground. The variation of the kinetic energy of the particle with height h is h as measured from the ground is best represented by. So you measure the height from the ground. Okay. So now this is the ground. So there is a free fall of this object, particle of mass small m. So now it's falling. Okay. So now you know it loses its potential energy and that is converted into its kinetic energy. So usually when we talk about potential energy, you should have a zero level of potential energy. So now I'm going to take this level, land level, as the zero level of potential energy. So H measured from here is 0. So it falls from a height of h0 now. So this I am just labeling. And randomly, if we take a height like h, sorry, h, just h, and it will have a velocity here and kinetic energy here. Okay. So now we are going to relate. We are going to relate the energies here and here. So according to the law of conservation of energy, yeah, what is the equation? So initial total energy is what? Small m g h naught. At this level, yeah. So you measure the height from here. So mgh plus its kinetic energy. So that's the equation. So we are asked the kinetic energy. So we don't have to substitute it with half mv square. Just keep it as ek. Okay, just make it easy. Yeah, ek is equal to, yeah, if you take this to this side, minus mgh plus mgh naught. So what is the equation for the graph? Y is equal to minus mx plus c. Yeah. So what is the shape of the graph? With positive intercept and a negative gradient. A linear graph like this. Okay. Okay. So what could be the answer if they ask the graph for the kinetic energy against the distance traveled? Against the distance traveled. Yeah. So it will be like this, no? Students, is it wrong? Did I write? energy H is equal to 0, it's maximum. Yeah, it's correct. Yeah, it should be like this, no? It is maximum. Maximum, kinetic energy is maximum. Yeah, it should be like this, no? Yeah. And what do you think about the EK with time? Hmm? What do you think about EK with time? Time measured from here. Yeah, from this point. Here T is equal to 0. Just please speak, okay? It's very boring for me also. Can you all tell me the answer for the graph? EK against time. This is how you should study. Huh? How?
Just like the graph of EK versus T.
With the time. So how are you going to relate the time with kinetic energy? You have the equation for kinetic energy. EK is equal to half mv square. And you know, here it starts from rest. So the initial velocity is 0. So for V, I can write it as u plus 8. You know, V is equal to u plus 8. U is 0. So AT. A is G here. So GT. So EK is equal to half mgt square. So EK is equal to half mg square t square. So for t square, it's a linear graph. Okay, it's a linear graph. So your answer will be correct. If the question was the EK graph against t, but the question is for t square. The question is for t. So it's like this for like acceleration. For example, if t is 1, t squared is 1. If t is 2, t squared is 4. If t is 3, t squared is 9. So observe the difference between these values. So here it's 3, here it's 5, and then it will be 7. Okay, so it should go like this. Okay, and try to draw for the potential energy also. So if this is for kinetic energy, for potential energy, it will be the other way. So if it is for kinetic energy, for the potential energy, this way. So here, how? This is kinetic energy for potential energy. Like this, okay? It's rapidly increasing and should rapidly fall. So like that. So this is how you should study. So you can answer the future questions. They are going to come this way. Sorry, students. Accident. Okay. Shall we go to the next question? Okay, next question is also a good question. Yeah, a solid cube of plastic of mass m, capital M, and side length 2x floats in water with half side length submerged as shown in the figure. If this cube is now converted into a hollow cube of mass same capital M with external side length 8x, the depth to which it submerges in the water will be. So you know the mass remains the same. So here, according to the law of flotation, the the weight of the water that is displaced should be equal to the weight of the object to float. Okay. So now the same amount of water, same volume of water should be displaced. That's the theory. Okay. So initially M, now also M, the shades. So the same volume of water should be displaced. So initially the cube, initially the one side of the cube is 2x. Now the length of the one edge is what? 8x. Okay, 8x. So length, width, height, everything should be considered. You should imagine an object like this. Okay, so this is also 8x. So now the same volume should be displaced. So here the volume displaced is this. So this is x. So what do you think about the area of cross section here?
4x squared.
Yeah, 4x squared. Yeah, 4x squared. So this is 4x squared. The volume displaced is the area into the height submerged. Okay. Here, what is the area of cross section?
64x squared.
Yeah, 8x into 8x, 64x squared. So 64x squared into, yeah, for the volume, you have to multiply by the height. So now the height is what? X over 60. X over 60. So the idea is the mass remains the same. So the volume displaced should also be the same. 12th question is a very interesting question. Okay. Everybody for the first time, okay, did this question wrongly. Okay. Because yeah, it has some confusion in it. Not a confusion, we confuse. Okay. So a Gaussian surface S encloses a metal sphere carrying a charge of plus Q. 3 n-type semiconductor pieces, each having a number of free electrons corresponding to the charge of minus Q, and 1 p-type semiconductor piece having the number of holes corresponding to the charge of plus Q as shown in the figure. Total electric flux through the surface can be made 0. So first, we shall discuss about the Gaussian theory. Okay, Gaussian theorem. So what does that say? Huh? What does that say? Can somebody tell me? So there's a charge plus Q. Okay, here. Only this charge here. So if you imagine a Gaussian surface, it says that the net electric flux through that Gaussian surface is the net charge multiplied by 1 over epsilon naught. Okay, that's the Gaussian theorem. Okay, so this epsilon naught is actually a constant. So electric flux is directly proportional to the charge enclosed. So now in our system, there is a plus Q charge and three n-type semiconductors and 1 p-type semiconductors. And they also put forward a very confusing statement that the n-type semiconductors, okay, n-type semiconductor pieces, each having a number of free electrons corresponding to the charge of minus Q. So what is that? Minus Q. corresponding to minus q is the free electrons corresponding to charge of minus q. What's the statement? Yeah, what is n-type semiconductor? You have two types of semiconductors. One is intrinsic semiconductors, the other one is extrinsic semiconductors. Intrinsic semiconductors are pure. Extrinsics are, they have an impurities. Okay. Impurity elements are added to intrinsic semiconductors to make extrinsic semiconductors. So there are two types of extrinsic semiconductor. One is N-type, the other one is P-type. So if you are going to make extrinsic semiconductor using silicon, to make N-type semiconductor, you may add something like phosphorus. To make P-type semiconductor, you should add something like aluminum. Okay. These are called electron donors. Okay, these are called electron acceptors. So these electron donors will give the extra electron to that lattice so that it will get one free electron due to one phosphorus atom. But here, these have only 3 valence electrons so that they will accept electrons from silicon and there will be a, but they can't afford to give one to silicon. So the hole will be left. Okay. They will actually share electrons, but there will be a hole left because they can only share 3. But silicon has 4 places. So one will remain as a hole. Okay. So hole is like a positive charge carrier. Electron is like a negative charge carrier. So usually the amount of charge can be expressed in coulombs. Okay. So now what they are telling is this has a charge, this has the free electrons corresponding to, having a number of free electrons corresponding to the charge minus q. So that means if the number of electrons, let's say capital N number of electrons in this N-type N-type semiconductor. So N into 1.6 into 10 to the power of minus 19, charge of 1 electron is equal to this q. Okay, so that is the meaning of that. So just to tell the number of electrons, just to quantify it, they are mentioning, they are relating this with q. That's all. But it doesn't mean that it has a resultant charge, a net charge. No, it doesn't have. Because the phosphorus will give a free electron to the lattice, but there is a proton. There is a proton that always neutralizes this electron. So this is this is never a net charge. That's just a free electrons, okay, dancing here and there. And hole is also like that. You can quantify by saying that it is the number of holes are similar to the charge of plus q, but you cannot actually consider those holes as a net charge. Okay, so they will not actually form electric field lines of flux. Okay, so they are just there. They are like substances, uncharged substances. So there is only one thing that you could do to make the net flux 0 through the surfaces. What's that one thing? Bringing what?
Minus q.
Yeah, a minus q. If you bring a minus q here, yeah, the resultant will be 0. So that's it. So bringing N-type, P-type semiconductors will not make any change. Okay, so it's only C that is true. The 13th question. 2 metal rods of A and B at room temperature are heated together. The expansions delta L are plotted with the increase in temperature delta theta. The 2 curves are found to coincide with each other as shown in the figure. This could happen only if. So now you know when you heat an object, the kinetic energy of the particles increases. So the particles are like performing what kind of motion? A simple harmonic motion. So when they increase their kinetic energies, the amplitude increases. Okay, so there is maximum displacement increases. So there is inadequate space for them, no, to oscillate. So they say, "Macha, what I get at the end of it." So now they are developing gaps in between them, so that what will happen? They will expand. So that's how expansion occurs. So expansion is depend on some factors. What are those factors? Yeah. So expansion delta L is directly proportional to L naught and also the delta theta. So delta theta is related to the kinetic energy. The temperature is a kind of measuring kinetic energy. Okay. And delta L, because if the delta L is high, there are so many people dancing like this. So they need more gap, isn't it? So that it's directly proportional to the L also. So now if you convert these relationships into an equation, you put a K constant. So that constant here is alpha. Alpha is linear expansivity of that element. Okay? Yeah. So now you can actually draw a graph for delta L against delta theta. So it will be a linear graph. So what are the determinants of the gradient here? Y is equal to mx. So this is m. So alpha into L naught is the gradient. So these two determinants are there. Two graphs, okay? For two graphs to coincide, what is the condition? The gradient should be equal, no? Gradient should be equal. So the multiplication of linear expansivity and the initial length should be equal to those two metals. So that, what's the correct answer? The fourth answer. You can't actually compare the alpha alone or L naught alone, because when there are two factors affecting the gradient, you can't actually comment on one factor. Okay, so there is the fourth answer, which is a perfect answer. The linear expansivity into original length is same for both fronts. So that is the correct answer. The 14th question. 3 coplanar forces of 20 Newton, 40 to the power 40 into root 2 Newton, 40 root 2 Newton and 30 root 2 Newton act on the particle situated at the origin O of a xy coordinate system as shown in the figure. The vector represents the force necessary to keep the particle stationary. So here, what is the idea? To keep that object stationary, there should be a force that is equal and opposite to the resultant force of that system. Okay, so now first you should find the resultant force. Am I correct? So how do you find the resultant force of those three forces?
Parallelogram method, sir.
Yeah, force parallelogram method. Okay, so if you draw parallelogram and see, finally you come to an answer OB. Okay, that should be drawn on the paper itself. Don't try to copy that in a rough sheet and then draw. Never try that, because your diagram may go wrong. So that is the purpose of giving these kinds of diagrams with a coordinate is this, to draw the parallelograms accurately. Okay, so now you can first draw a parallelogram for these two forces, and this is the resultant, and then you draw parallelogram for these two forces, and this is the resultant. Okay, so the force that should be applied to keep this object stationary should be opposite and equal to this force. Am I correct? So it is OB here. Please try to draw on the paper itself. Okay. The 15th question is open. The answer is open. Okay. A heavy roller of mass 500 kilogram moving on a horizontal surface at a constant velocity of 1 ms minus 1, as shown in the figure, stopped in 0.5 seconds on hitting a smooth vertical wall. The horizontal force exerted by the wall is. Okay, you can actually try to find an answer. How? How?
Newton's second law.
Yeah, Newton's second law. So according to the Newton's second law, you can derive an equation for F like this. That is rate of change of the momentum. So m into v minus u over t. Okay. So it stops. So the final velocity u is equal to 0. Okay. So the final velocity v is equal to 0. V is equal to 0. So the force acting on that particular object is in this direction. So I'm using the equation in this direction. So m is 500 kilogram. V is what? Final velocity 0 minus initial velocity is in this direction. So minus plus. Okay, so it will come as plus finally. Over t is 0.5 seconds. So what's the answer? Thousand newtons. Okay, so the answer is the fourth answer. Here the question is very clear because they say the velocity of 1 meter second minus 1 as shown in the figure is stopped in 0.5 seconds on hitting the smooth vertical wall. The horizontal force exerted by the roller on the wall is. So this is usually the force exerted on the roller by the wall. So the action and reaction will be equal in magnitudes. No? So that's also 100. Okay, so the 100 can be the answer. Yeah. Okay, I will clear. Yeah.
So on the previous question, can't we use some other method like using the square numbers on vertical direction and x direction and calculating them, and use some other method other than the parallelogram theory?
You can find the magnitude of the forces by using the method you are explaining. Yeah, that is also a good method. Taking components and then simplifying. No?
I mean, like, can we use this method in some other questions like this other than this? Or is it valid to use only the parallelogram method?
Yeah, for directions, if they are asking direction, the best ideal way is the parallelogram method.
Okay, so thanks.
Okay. The answer for the 15th one is the fourth answer, no? Yeah, in your past paper?
Yes.
Yeah, fourth answer.
Yeah.
Yeah, fourth answer. That should be because this was open in Tamil medium paper, okay, not in the English medium paper, because they didn't mention the stop thing in the Tamil medium paper, so that it was given open marks for everyone. Okay, because they didn't say stop, so the final velocity is not given, so you cannot actually solve the problem. So that was the problem, but here it is mentioned, no? So I thought the same answer was given to this source, so sorry for that. Okay, so 16th question. 16th question is also very easy. Traditional grain grinder consists of two flat stones. The upper stone is rotated on the top of the lower stationary stone by applying the horizontal force of magnitude F, and handle H is fixed at a distance of R from the axis of rotation as shown in the figure. If the force is always applied parallel to the direction of the motion of the handle, the period of rotation T and the period of rotation is T, the power being expended is, yeah, there should be a power expenditure when you are rotating or moving something against a resistance. No? For here it is rotational motion. So what kind of resistance you have? It is your torque. Okay. So in linear motion you have force, but here it's torque. So yeah. So usually the power is the rate of expenditure of energy. Okay. Okay. Or work done per unit time. So in linear motion, it is force into the distance, but here it is torque into theta. Okay, divided by the time. So this is omega. So torque into omega. But it should be mentioned that there is a constant angular velocity. So it should be it should be a constant angular velocity. Here also it is mentioned like this, because the period of rotation is t, that is constant. So omega is equal to 2 pi by t. No? So if it is constant, and this also should be constant. Okay. So now you are going to substitute for the torque and omega. So what is torque? Torque is force into the perpendicular distance from the axis of rotation. So F into R. So what is omega? 2 pi by t. Very simple. The answer is first one. Then 70. Radioactive material has a half-life of 60 minutes. The percentage of the fraction of the material that has decayed during this period of 3 hours is 3 hours. So what is the idea here? So you know the radioactivity. So the radioactivity is actually the emitting the radioactive substances. So radioactivity occurs due to the unstable nuclei. So there are three types of radiations that we study: alpha radiation, beta radiation, and gamma radiation. So you should know the instances. I mean, you should know the change of the mass and the proton number when these products are emitted. Okay, so that is another thing. So when a radiation occurs, you actually lose nucleus, no? So initially, the initial number of undecayed nuclei was n, and after some time, you will see less undecayed nuclei. Why? Because some have decayed. So if you draw the graph for undecayed nuclei against time, it will come like this. Okay, sorry, it will come like this. You will never find a time where there is no undecayed nuclei. Why is that? Because this reaction is a what kind of reaction? What order? What order reaction? There are orders of zero order, first order, second order. What kind of order is this? In chemistry, here the rate of reaction, here we mention this as A, activity, is directly proportional to the number of undecayed nuclei. Okay, so this activity can also be expressed like this: dN over dt is directly proportional to n. Okay, okay. So when the number of nuclei decreases, the activity also decreases. So let's make an equation using this. So you have to put a constant. So you put a constant called lambda. So that is called what's the name of this? Decay constant. Okay, decay constant. And there is something called a half-life. So what is half-life? Half-life is the time taken. Okay, time taken for the number of undecayed nuclei to become halved. Okay, so for example, the number of nuclei here at this point is n naught. So at one point it will become n naught by 2. So the time taken for that is called the t half. So again, after some time it will be half n naught by 4. The time taken for that will be again t half. So in this axis, this will be 2t half. Okay. And again in 3t half, it is n naught by 8, isn't it? The t half is actually a constant. Do you have any equation for t half? Do you have any equation for t half? What is the only thing that affects t half? Quick. We are running out of time. What is the only factor that affects t half? That is this lambda. No, it's 0.693 over lambda. That is equal to t half. So lambda is the only factor that affects t half. So t half is a constant. So here the t half in the question, t half is 60 minutes. And they are asking the percentage of, the percentage of the material that has decayed during the period of 3 hours. So 3 hours is 3 times 60 minutes. 60 minutes is 1 hour. So 3 half-lives. So for each half-life, the number is half. So it was half and again half and again half at the end of the 3 hours. So now it is the 1/8 of the initial amount that is remaining. Okay. So what is the percentage? If you multiply it by 100, you get the percentage that is remaining. So this is 12.5%. We get 12.5%. So what is the percentage that has decayed? That is 87.5%. Okay. So that is fifth answer. Okay, let's discuss the 18th question a little bit deeply. So do you have any doubts here in this question? No? Okay, then 18th. What is the unit, SI unit for radioactivity? Tell.
Becquerel, BQ.
Becquerel, yeah, BQ. Yeah. Then 18th question. Intensity of the noise generated by a machine is 10 to the power of -2 watt meter -2. By employing the noise barrier, the intensity of noise is reduced to 10 to the power of -6 watt meter -2. What's the reduction in the noise intensity level? So you know something called sound intensity of sound. So intensity, okay, can be defined as the energy that passes through a unit area in a unit time. Okay, so it is actually the energy divided by the area and the time. So here the E over T is actually the power. Okay, so power over area is like a broad definition or equation, saying broadly for intensity, for any intensity. For sound also it's applicable. So let's consider a point source of sound. So it's creating a sound. So the sound waves will spread like this. These are waveforms. Okay, waveforms. So it takes the shape of what? Shape of a sphere, isn't it? Okay, you should imagine it's 3-dimensional. So it's shape of the sphere. Actually, the power of the noise or sound that is emitted remains unchanged. It is not absorbed or it's not lost. So the power of this wavefront is equal to the power of this wavefront. But there's one person standing here and the person standing here. Will hear the sound differently because the power that is passing through a unit area differs. Because here the area is less, but here it has spreaded through a larger area. So this, for example, the radius of this sphere is R1. The radius of this sphere is R2. Can you tell me the equations for intensities at this level I1 and intensity at this level I2? Equations. You know, P remains unchanged. So P is okay. So now the question is the area. Tell me. Please tell me. Okay. Easier question. You're going to disappoint me. The equation for the area, simple. Area of the sphere, 4 pi r squared. Okay. So here it's 4 pi r1 squared and here is 4 pi r2 squared. So the intensity is directly proportional to 1 over r squared and intensity is directly proportional to P. Okay. So these are some relationships. But yeah, when you calculate the intensity, it is like very much varying. For example, it ranges from 10 to the power of minus 12 to 10 to the power of, for example, 8. Okay. So within this range, it is very difficult to use the intensity. So we introduced something called intensity level. Okay, what's that? Intensity level beta is 10 log I over I naught. What is this I naught?
Threshold level.
Threshold level. Yeah, threshold level for your hearing. This I is the given intensity of the sound. This beta is intensity level. This I naught is always 10 to the power of minus 12. So now we are going to derive an equation for the difference between two intensity levels. For example, there is an intensity of I1 and intensity of I2. The corresponding intensity levels are beta 1 and beta 2. So what is the equation for beta 1 minus beta 2? It is 10 Lg. Yeah, if you subtract these two, when they come, I mean, when you take log, you actually divide it. So I1 over I2. But you know that the I is related to the distance and power like this. So you can derive some equations in relation to the distance and power. So 10 log R2 squared over R1 squared. Yeah, it's other way because it's indirectly proportional. Okay, directly proportional to 1 over R squared. Okay, or indirectly proportional to R squared. So 10 Lg for power in relation to power P1 over P2. Okay, so these equations should be remembered, and you should never use rough sheet when solving these kinds of problems, because we expect you to solve these problems by using solely by your brain. Okay, it's very easy. These calculations were never difficult. Yeah. So here, how is it reduced from 10 to the power of minus 2? From 10 to the power of minus 2 to 10 to the power of minus 6. So difference in intensity levels. So just difference. Okay. So when you substitute these two intensities here, so I1 over I2 is 10 to the power of minus 2 or 10 to the power of minus 6, 10 to the power of 4. When you take log 4, when you multiply by 10, 40. So 40 decibels. You should never write the calculation. Okay, understood. Okay, please revise all this theory. Okay, then 19th question. A convex lens is used to obtain a clear image of an object on a screen. So it should be a real image. The screen is located 30 centimeters away from the lens and the object is 12 centimeters from the lens. If the lens is now used to focus the image of a distant tree on a screen, distance between the lens and the image of the tree is. Now they are talking about tree, isn't it? Now they are talking about tree. Initially they were talking about some object. It's so confusing. Okay, not like that. Okay, that's how they want you to think, but you should never get confused. So now first, let's analyze the first part of this question. The screen is located 30 centimeters. So it should be a real image because there is a screen that is on which the image is displayed. So it should be a real image. So the distance between the image and the lens is 30 centimeters. And the object is 20 centimeters. So it should be in the other side because it's a real image. So it's the object. So there'll be image somewhere here. Okay. So now you can actually find the focal length of the lens. And then when you're observing the image of a distant tree, so distant means it is at the infinity. So what is the so what can you say about this? Where would the image be formed? If we have the object at infinity, you get parallel waves. Okay, parallel rays, sorry, rays. So then where do you get the image? Huh? Where do you get the image?
Focal point.
Yeah, focal point. Yeah, so this is where the screen should be kept. Okay, that's it. So you should find the focal length. Okay, you should find the focal length. So what's the equation? 1 over b minus 1 over u is equal to 1 over f. So first, you have to apply the sign convention. For real images, always it is 1.1 over v plus 1 over u is equal to 1 over f. We know that. But for explanation purpose, I'm explaining this. So v, this side is minus and this side is plus. So here, this is minus. And this is plus, there's already a minus, and focal length is minus. So it's 1 over v plus 1 over u is equal to 1 over f. So 1 over v is 30. 1 over u is 20 is equal to 1 over f. So what is f here? Huh? 12 centimeters. Okay. So that is the answer. 12 centimeters because you get the image at the focal point. Okay. Then 20th. Which of the types of the glass prisms shown in the figure 2 can be used to bend the ray of the light into all forms given in the figure? So here, as you observe the ray diagrams, what is the deviation of the rays? Huh? What is the deviation? In all the images, what is the deviation?
90 degrees.
90 degrees. What is the only prism that can produce 90 degree of deviation? That should be
45, 90, 45 this.
yeah, 90, 45, 45 prism. Okay. So you know that by theory, this 45 degrees, 45 degree. So to make a deviation of 90 degree, it should be set like this. So here the incident angle is greater than the critical angle. So you get reflection like this. Okay. Okay. That's it. And this is 90 degrees. Okay. So what will happen for figure 1 and 2? Figure 1 is 60 degrees. It's a equilateral angle, equilateral triangle prism. So you can send like this, okay? So what is the incident angle here? It is 60 degrees. It will undergo total internal reflection. But here you will have this is what 30 degrees and 60, so it is no reflection. So you have a deviation of 120 degrees. And for the second diagram, this is 30 degrees, this is 60. Okay, so if you send something like this, you will have, but here also you will have some refraction. So never 90 degree of deviation. And can you get a 180 degree of deviation in right angle triangle prisms? 180 degrees? Yeah, can you? Can you get it? Yes, if you send like this, you will get. So 90 degree, 180 degrees, they are always possible only in a 90, 45, 45 prism. Okay. Then a very interesting theory comes. 21st question. Okay. What is that? Photoelectric emission. Sorry, photo emission, photoelectric effect. Okay, so 21st. The work functions corresponding to two metals A and B are W1 and W2. What is work function? Work function is the minimum energy that a photon should have to remove an electron. Okay, to just remove the electron from a surface of a metal. So the W1 is greater than W2. The two surfaces made of A and B are illuminated separately using a monochromatic beam of light of frequencies F. Which of the following graphs correctly represents the variation of the maximum kinetic energy Ke maximum of the emitted photoelectrons with frequency F and the incident light beam for the frequency F of the incident light beam for the surfaces made of metals A and B. So now let's explain this theory. Okay. So do you know about a photoelectric cell? Huh? A photoelectric cell like this. Yeah, we have a cathode and an anode. So this cathode is made up of what? A metal. And you send some photons, a light beam, okay? So it comes and strikes this metal. So these photons will have a photon energy, which is equal to hf, or it can be expressed as h over lambda. If it is greater than the work function of that particular metal, they can actually remove electrons. The electrons will be emitted. Okay. Sometimes the HF is equal to the work function. So at that point, this frequency is called a threshold frequency. So this can be defined as the least frequency that a wave or a ray should have, a light ray should have to remove electrons from a metal. Okay, metal surface. So this is called the threshold frequency. And also you have threshold wavelength, which can be expressed in an equation like this. Okay. Sometimes this relationship is there. I mean, the photon energy is greater than the work function. So what happens to the remaining energy? It is converted into the kinetic energy of the electron. So we can balance the energies like this. HF is equal to the photon energy is spent for the work function and also for what? The kinetic energy. Usually we define the work function as what? The minimum energy needed, no? So this kinetic energy is maximum kinetic energy. So you give the minimum to this metal and the Ke will be maximum. So this is the final equation. So can you relate Ke with something else in a photoelectric cell? Do you try to give some voltage to manipulate the movement of electrons? Huh? Do you give some voltage? Yeah, you give. So at one point, you will not see any current flowing through the circuit. So at that point, the voltage difference between these two electrodes is known as the stopping voltage. So the work done by that stopping voltage is the stopping voltage into the charge of the electron. Because this is on a unit charge. So to find the work, we have to multiply it by the charge. So 5 plus VSE is the final equation. Okay. So now the question is the graph for this kinetic energy against the F. So just make Ke maximum as subject. So now HF minus 5. So Y is equal to Mx minus C. So these two different metals have different work functions. So they will have different intersects. Okay, but they have the H is same. Okay, so H is same. So that the gradient should be equal. So the graph should be parallel to each other with different intercepts. So like this. So this should have a lesser intercept and this should have a greater intercept. So this is the graph for the greater work function, that is the metal A, W1. So this should be for A, this should be for B. Okay. And you will also be asked to draw graph for Bs against H. So for that you have to make Bs a subject. So this will go and divide HF and also 5. So H over E into F minus 5 over E. So now again the gradient is going to be equal for both metals, but the intersect is going to be different. So whatever the question, you can actually draw a graph. So let's draw some other graphs also. Okay. What are the other graphs? Yeah. Let's change frequencies, keeping the intensities of the light equal. And now let's change the intensity for a monochromatic wave. Same color, same frequency, but different intensities. Different frequencies, same intensity. So F1, F2, F3, the relationship is like this. And I1, I2, I3 intensities. But F is same, monochromatic, but different intensities. So what would be the answer? This is the IV graph, okay? IV graph. Okay, try drawing, okay? So here I will give an idea. Intensity directly affects the current. If the intensity is equal for all three waves, all three rays, the current will be, the saturation current will be equal. But the F will affect the stopping voltage by affecting the kinetic energy, maximum kinetic energy. So for greater F, you will get a greater stopping voltage. Okay. And when you consider this question, the I1, I2, I3, according to I1, I2, I3, the saturation current will not be the same, but the stopping voltage will be same because same F. So here the graph will be like this. This is phi 1, this is phi 2, this is phi 3. Here the graph will be like this. This is phi 1, this is phi 2, this is phi 3. Okay. So I can told the answer also. Just revise the theory and try to prove. 20 seconds. Two ends of two identical metal rods of uniform cross section are placed very close to each other, and those ends are heated using an electric heating element which supplies heat at a constant rate of P, as shown in the figure. The rods are thermally well insulated as shown, and at the steady state, the temperature at free ends are exposed to surroundings is T0. Assume that the entire heat energy generated by the element is absorbed equally by two rods. Even if they don't give that, as the diagram is symmetrical, the system is symmetrical, the power is going to be distributed equally. Assume that entire heat energy generated by the element is absorbed equally by two rods. So if the rate of heat generation is P, one is going to get P by 2, the other one is also P by 2. So if A, L, A, and K respectively are length, cross-sectional area, and thermal conductivity of a rod, what is the temperature of the ends of the rod close to the heating element at the steady state? So you know, at a steady state, you can apply an equation for the rate of flow of heat in a what kind of system? It should be insulated or lagged. Okay. Yeah. The sides should be insulated. So there is only the axial flow of heat. So you can now write an equation. If the length is L, the temperature difference is here, theta and theta, so theta minus theta 2. The rate of flow of heat is Q over T. If the thermal conductivity is K, the equation is Q over T is equal to Ka into area of cross section is A, theta 1 minus theta 2 over L. So this is thermal conductivity. This is area of cross section perpendicular to the rate of perpendicular to the flow of heat, and this is the temperature gradient, temperature difference divided by the length. At a stable state, this is constant through constant along the length. Okay. So now here we are going to apply. So here there is a heating element, and here one side and the other side identical rods are there, and the heat is absorbed equally. So if it is producing the heat at the level of P, at the rate of P, this is P by 2 and this is also P by 2. So how are you going to substitute this in the equation? So P by 2 is equal to K, A. This theta 1 minus theta 2 is T minus T, no? Divided by L. So if you make T a subject, what is the answer? T is the question. What is the answer?
T equals T naught
T naught
plus
plus PL over
PL
2KA.
K.
2KA. No? Good. So the second answer is correct. Okay. It will take some time. Okay. I mean, I will finish before 9:30. Okay. So next question, I'm going to revise the theory for that also. Okay, an ideal gas can expand from state A to state C along three thermodynamics paths, ADC, AC, and ABC, as given in the PV diagram. Along which of the following above paths would the highest exchange of heat occur? So, you know, the first law of thermodynamics. The first law of thermodynamics says that delta Q is equal to delta U plus delta W. Okay, what is delta Q here? Delta Q is heat exchange. If it is given to the system, that is in plus. If it is emitted from the system, that is minus. Delta U is what? It is increase in the internal energy. Oh, that is kinetic energy. I already explained you in the first question. So if it increases, it's plus. If it is going to decrease, that is in minus. What is delta W? Okay, you tell what's delta W?
The work done by the gas or on the gas.
Work done by the gas or on the gas. Yeah. If it is done by the gas, it is in plus. If it is on the gas, it is minus. No?
Yeah.
So usually the delta U is related to temperature because you know the kinetic energy is N 3/2 nRT. No, so it's directly proportional to T. So we can write delta U is directly proportional to delta T. And delta W is related with what? The volume change. It is not directly proportional or something, but if the volume change is plus, delta W is also plus. There is no a proportionate relationship. Okay? There is no proportionate relationship. You should be able to apply this equation in questions and also you should be able to explain the processes. Okay? There are 4 types of processes that you should know. Okay, I will briefly explain. What are those processes? One is isothermal. In isothermal, the temperature change is 0. So here the internal energy change is also 0. Okay. So here, because the temperature is constant, the gas follows the Boyle's law. So the PV graph will be like this. Okay. So this is an isothermal change. So because the delta U is equal to 0, delta Q will be equal to delta W. Okay. So you should always mention the direction. So if it is like this, what is the sign of delta W?
Minus.
Increasing volume. So it's plus. So delta is also plus. If it's the other way, the delta W is minus, delta Q is also minus. So this is the process number 1. The second process is what?
Adiabatic.
Adiabatic. Adiabatic change. So here you have what is 0 here? Delta Q is 0. So usually in an adiabatic process, if you draw a PV graph, the graph will be similar to this graph, but the change of the pressure is high. So if this graph is like this graph is like this. So if the isothermal change is like this, the adiabatic change will be like this. The pressure difference is high. So here also you can actually say the signs of the delta Q and the delta Q, delta W, delta U. So for example, if the volume is increasing, what's the equation? So here delta Q is 0 no. So delta W is what? Minus delta U. Am I correct? Minus delta U. So the volume is increasing. So what's the sign of delta W?
So excuse me, I could
Plus.
Okay.
Delta U minus. Okay. So there will be reduction in temperature. Okay. There will be reduction in temperature. So if it's the other way, the signs will get the opposite. The signs will be opposite. So what is the third change?
Isomeric or isoporic?
Isochoric. Isochoric is also for constant volume. No, you said that. So here the graph is either like this or like this. So here delta W is what?
0.
Good, 0. Because there's no change in the volume. What do you think about delta Q and delta W? Delta U. Here. So here, constant volume, the pressure has increased. So what should happen to the temperature? In PV is equal to nRT. Constant volume, pressure is increasing. The temperature should increase. So delta U is plus. Delta Q is also plus because as delta W is minus, delta Q is equal to delta U. Here, it's decreasing. So it should be minus, it should be minus. The other process, last one, fourth one.
Isobaric.
Yeah. Isobaric. Isobaric is constant pressure. So it can either be like this or like this. So here the volume increases. So delta T should be plus. Here the volume decreases. Delta T should be minus because in PV sum and nRT, if the volume is increasing without a change in pressure, so the temperature should increase. Okay, so you can say the delta W is plus, delta U is also plus. So delta Q should be also plus. Here the other way. Okay. And how do you find delta W in a PV graph? The area under the graph is delta W. Okay. So here in this graph, the area under the graph is delta W. So if it is increasing, volume is increasing, the A is positive. Okay. Okay, then. So here there are 3 changes starting from 1.2 ending in the same another point, A to C. So all finally come to C from A. So what component is equal for all those 3 processes? Huh?
Delta U.
Delta U, internal energy change, is equal. Why? Because it is only dependent on the initial and final points. Okay, it is not dependent on how the change is brought about. It is dependent only on the where it starts, where it finishes. So even if it is like this, it can be like this, it can be like this. The delta U is same. So when comparing delta Qs, as in the question, they are mentioning that heat exchange would occur, highest heat exchange. So what's the factor that determines delta Q? Delta U is same. So delta Q is equal to
Delta W.
delta Q is equal to delta W plus delta U. Delta U is equal for all 3. So delta W is the determinant of delta Q. So delta W is the area. So area is highest for what? A, B, C. So this is the area for A, B, C. For A, C, this is the area. For D, C, this is the area. Okay. So the highest delta Q would be for A, B, C. Okay. Because the highest work done is there. Okay. For 24th question, the same current I is sent through the resistor networks A, B, and C as shown in the figure. If all resistors in the network are of equal magnitude, the maximum power is consumed by, the I is equal for all 3 networks. So what is the best equation to use for P?
I squared R.
I squared R. Yeah, very good. I squared R. So for A, so we have to think about R. So which network seems to have highest R? C, because they are connected serially. So for C, if we say the equivalent as RC, it is 4R. For B, the equivalent will be less than R because the rest of the system is connected to the first resistor parallel. Okay, the rest is connected to the first resistor parallel. So the equivalent will be less than the R. Okay, so for first one, A is also like that. The value of the equivalent resistance will be between 2R and 3R. Okay. Okay. So 2R is connected serially, so it's greater than 2R and less than 3R. So they can't beat the C network. Okay. So the C is the correct answer. And then the other questions we shall discuss tomorrow. Okay. So it's like, yeah. Do you have any doubts in any part of the physics or here in the paper? You can ask any doubt if you have.
So I going to conduct, cover the papers or else doing some lessons other than this? Or like I'm going to do the papers, explain the MCQ review or else do other classes other than this?
No, I can hear you, but I couldn't hear the words clearly.
Will you be doing the papers or classes, conduct classes other than this?
Other than this means without papers. What kind
Yeah.
of classes? Theory.
Yeah, theory class. I don't have covered the last syllabus, matter and radiation. So, wanted to.
I don't think so because yeah, this is difficult for me a little. I have finished the syllabus already for Tamil medium. I have never tried for English medium teaching theory. I don't have notes also. That's the problem. I don't have time also.
Okay, so
I'm
then
not sure whether I'm going to continue this class also. But I will continue because I will continue teaching English medium students. But as a class, it depends on the situations. Okay. So we will like finish the years one by one and I will explain the relevant theory for that question. And if you have doubts, you can ask me. And it's better if you can understand the Tamil medium classes. I have videos, all the videos for metal and radiation. You can, if you can actually, you can use those videos. But if you don't understand Tamil, that will be difficult.
Okay, so sure, I'll try.
And other students, any doubts? I know the first part of the paper will be boring, okay? Sorry if it was. Thank you. Thank you for your patience. And I will check the chat.
Thank you, sir.
Okay, so thank you.
Thank you, sir.